load is spread throughout the diagram or spread throughout the beam, and it carries the magnitude or intensity of 2 kilonewton per meter. Okay, so that is the magnitude of the UDL or uniformly distributed load. So what you need to do now is to take this 2 kilonewton meter and multiply it with the distance that it covers. Okay, in this diagram we know that it covers the full beam, and we know the total distance of the beam is 5 meters. So 2 kilonewton per meter multiplied by 5 meters will give you 10 kilonewton of a single force or a point load. Okay, so that 10 kilonewton of point load will now cancel off all this UDL. Okay, we'll cancel off all this uniformly distributed load. Okay, and will be represented by a single arrow in the middle of the distance that it covers, which is in the middle of the beam. So I'm going to use the purple ink to show you that. So that should be 2.5 meters somewhere there. That will be 10 kilonewtons. Okay, just to refresh, just to recap what we just did. Initially we had a uniformly distributed load which was distributed throughout the diagram from pivoting point A up to pivoting point D. And what we did was we tried to simplify that by multiplying that with the distance that it covered. So we know that it covered the whole distance of the whole beam. So we multiplied 2 with 5, which gives you 10 kilonewton. And this 10 kilonewton has to be a single load or a point load that will be situated in the middle of the diagram. You have to point that in the middle of the diagram or in the middle of the distance that it covers. Okay, so it is there at 2.5 meters from both ends. Okay, now we will work through this problem as usual. Okay, from what you did from the previous video, you know that you have to now choose one point as your pivoting point. We are now going to choose point D again as your pivoting point, and we're going to take all these forces, multiply it with perpendicular distance, and redirect that or direct that to point D or your pivoting point D. Okay, we know that the total moment about the system will be equivalent to 0. So rotating anti-clockwise, assuming that that is positive. So moment about point D must be equivalent to 0 because the system will be in equilibrium. Okay, it's a static system. It's not moving, it's not bending, it's not having any kind of motion at all. Alright, so let's try and work this out. We have RA multiplied with the total distance or the perpendicular distance, which is 5 meters towards point D or your pivoting point D. And that has to be positive because this RA is rotating clockwise. Alright, and then the second force that we'll be looking at is this 5 kilonewton. 5 kilonewton is pointing downwards, and the perpendicular distance between this 5 kilonewton to the pivoting point D is this 3 meters over here. So minus 5 kilonewton multiplied by 3. Why it's a minus? Is because it is rotating anti-clockwise. Okay. And then the third force that we'll be looking at is this 10 kilonewton force, again pointing downwards. Okay. So usually when it's on top of the diagram, yeah, it will be always pointing downwards, which is why I always like to use an arrow. Let's assume that this question was, was simplified to a uniformly distributed load like that. Okay, so just use the same direction as that. Okay, so this 10 kilonewton force has a perpendicular distance of 1.5. Sorry, it has the perpendicular distance of 2.5 meters, doesn't it? Because it's sitting in the middle of the 5 meters. So that is minus 10 multiplied by 2.5. Okay, lastly 7 kilonewton pointing downwards again, minus, and it's minus because it's rotating anti-clockwise, so 7, sorry, multiplied by 1, which is the perpendicular distance. So I'm not going to use the kilonewtons there because now it's going to confuse you. Just force times distance, force times distance, force times distance. Okay? So that gives you, if you solve for it, I do not have a calculator on me right now. So find your RA. Okay, so once you've found your value for RA, you will then use that value over here. You just put RA